Okay. So I am Debojyoti Kaur. So I am doing my PhD from Indian Institute of Science. So I would be the TA for this course. So I did my bachelor's from IIT Kharagpur from the Department of Computer Science and Engineering, and currently I am doing my PhD in Computer Science and Automation Department in IISc. Okay. So today my plan is to go over some common problems. So the topic for the first week is mainly pigeonhole principle. So my goal today is to go over some problems, some basic problems on this topic. Which so these problems, if you had taken a look at the lecture, if you had taken a look at lecture 1, these problems were the homework problems in that. So yeah, we can. So let's start with this. And at any point you can unmute and ask questions, or you can write in the chat. I want this to be as interactive as possible. Okay, and if you have any doubts at any point, then please interrupt me. Okay. Okay. So let's look at the first question. So what is this saying? That let S be any n plus 1 element subset of the first 2n natural numbers. So which means out of the first 2n natural numbers, we are picking arbitrarily any n plus 1 elements. Now the question asks, we need to show that there are two elements A and B such that A divides B. And secondly, we also need to give an example of an n element subset of these numbers without this property. Okay, so the first part, what is it asking us? That among the first 2n natural numbers, if we pick any n plus 1 numbers arbitrarily, then there always must exist two numbers A and B such that A divides B. Okay, so how do we solve this? Okay, yeah. Okay. Yeah, Tejashree, do you want to ask something?
No, I was thinking of the answer.
Yeah, sure, yeah.
We can group them as there will be n like n by 2 odd and n by 2 even
Yes. I mean
integers.
n odd and n even, because there are two n numbers. So n odd and n even
Oh,
numbers.
this yeah.
Yes.
Yeah, I'm talking about the n plus 1 subset.
Okay. Okay.
In
No,
that
so that subset
one
is
is x.
chosen. That subset is chosen arbitrarily. So I mean, it is possible that all, let's say, n numbers are even and only one number is odd. That we do not have any control over.
Okay, okay.
Yeah. So we have to show that no matter which n plus 1 elements we pick, there will always exist two elements A and B such that A divides B.
Yes.
Okay. So here the trick is, so now consider any number. So any number can be split into an odd part and an even part, right? So let so suppose you have, let's look at an intuition. So suppose you have the number 36. So now if we do the prime factorization of 36, it is what, 4 into 9, that is 2 squared times 9. So 9 I am not splitting further. So here 2 square is the even part of 36 and 9 is the odd part of 36. So in general, given any number, we can split it into two parts. One is a power of 2 and the remaining part is a odd number, right? So let's write this down. Okay, so right, and this representation is unique. Okay, now the thing to note is that suppose there are two numbers whose odd parts are the same, right? So let's say we have two numbers, let's say 2 to the power k1 times b, and there is 2 to the power k2 times b. and where this number b is odd and is same for both the numbers, then in that case we can surely say that either one of these numbers will divide the other. So if k1 is less than k2, in that case 2 to the power k1 times b is going to divide 2 to the power k2 times b. And if it is the other way around, if k2 is smaller than k1, then 2 to the power k2 times b is going to divide 2 to the power k1 times b, right? So now, in order to show that a divides b, what we need to show, it is sufficient to show that out of these n plus 1 elements, there will always be at least two numbers whose odd parts are the same, right? So okay, so once we show this, we are done, because then one of the numbers will have a smaller even part, and that is going to divide the number with a larger even part, right? So we just need to show this, that out of these n plus 1 elements, there will be at least two elements whose odd parts are equal. Okay, now since all these numbers are between 1 and 2n, so what are the possible odd parts? So this is the set up to 2n minus 1, right? These are the possible, since every number is less than equal to 2n, so the odd part of the number has to lie in this set. It's an odd number which is less than equal to 2n minus 1. So these are our wholes, right? And so how many such numbers are there? There are n such numbers, so n wholes. Okay, so now we have picked n plus 1 elements. These are our pigeons, and now there are n wholes, so which means there must exist two numbers whose odd parts are equal, and so we are done. Right? So the first part is done. Now we need to show, the second part says that we need to give an example of an n element subset which does not have this property. So we saw that if we pick n plus 1 elements, then there will always be two elements such that one divides the other. And now we have to show that if we pick n elements, so there is a way of picking n elements out of these two n elements such that no number divides any other number, right? Okay, so then as we saw here, so there are n wholes. So if we had picked n plus 1 many numbers, then like two of them must go to the same hole. So now if we are picking n numbers, the first thing that we want is that all of them should go to distinct holes. There are n holes and n numbers, and all of them should go to distinct holes. Otherwise we will have two numbers such that one divides the other, right? So then these n numbers, we know the odd parts of these n numbers. The odd parts must be 1, 3, 5 up to 2n minus 1. Now we just need to somehow construct the even parts of these numbers so that no number divides any other number. Okay, so how do we do this? Okay, so let's say we start with this. Okay, so these are the odd parts of the numbers. Now we are going to iteratively construct our required set of n numbers. So what are we going to do? So we are going to start with this, then Okay, so what are we doing? As long as we get to, in this we are starting with this sequence. Now as long as we get two indices, two elements of this sequence such that one divides the other, what we do is just we double the smaller number, we double the number which is dividing the larger number, right? And we keep on doing this. Okay, so first of all, so now we need to argue about the correctness and the termination of this algorithm. So now first let us argue why this algorithm should terminate. Okay, so now my claim is that, yes, you can ask.
Sir, I had a doubt. I
Yes,
didn't get the first question. Could you
yes,
just
yeah. Sorry, you want me to repeat which part?
these n holes part?
Okay, so as I said, any number, if you look at the prime factorization of the number, so it is 2 to the power something times 3 to the power something times 5 to the power something and so on, right? So what I am doing is I am just grouping this 2 to the power something part and the remaining part is an odd number, right? So if we take any number, so for example, let us take the number, I mean, let's say 500. So what is this? This is just uh, wait, so if we look at the prime factorization of this, so 100 into 5, this, so 500 can be written as 2 square times 125. So here 2 square is the even part of 500 and 125 is the odd part of 500, right? So what are we doing is we are just uh, considering what is the maximum power of 2 which divides the number. So any number, it can be split into 2 to the power that thing times the remaining part, it has to be an odd number, right?
Yes.
Yes. Okay, and now what I am saying is that since all these numbers are less than equal to 2n, so what are the possible odd parts of the number? It has to be an odd number in this range. The maximum possible odd value is 2n minus 1 because all the numbers are less than equal to 2n, right? So these are our n holes. Now if two numbers, consider any two numbers a and b which have the same odd part, which means a is of the form some 2 to the power k1 times, let's say, L, and b is of the form some 2 to the power k2 times L. Assume that both of them have the same odd part. Then in that case, from among these k1 and k2, one number has to be less than the other. So let's say, without loss of generality, k1 is less than k2. So in that case, 2 to the power k1 times L is going to divide 2 to the power k2 times L, right?
Yes.
Okay, so then what we have is we have n holes. These are 1, 3, 5 up to 2n minus 1. These are our n holes, and we are selecting n plus 1 numbers. So then obviously by the pigeonhole principle, there must be two numbers whose odd parts are the same, and then one of them must divide the other. Okay,
Yes.
is it clear? Okay, and now the second part says that, so here we had picked n plus 1 numbers and we had to show that two of them divide the other, and the second part says that this is type, that is, if we pick n numbers, then this condition need not be true. That is, we have to construct an example, construct an instance wherein we are selecting n numbers out of the numbers 1, 2, 3 up to 2n such that no number divides the other. Okay, so now in that case, again there are n holes. So if we want that the n numbers not to divide each other, then all these n numbers must go into distinct holes. Otherwise, we would again have one number dividing the other. So that is why what do? We start with this sequence 1, 3, 5 up to 2n minus 1. Now, as long as we get two indices I and j, as long as some element of this sequence divides some other element, we double the smaller element, right? And we return this sequence. So now my claim, so we are selecting n elements, and now my claim is that these n elements satisfy this property that no two numbers divide each other. So first of all, you need to show, so since we are doubling these numbers, it might happen that a number becomes more than 2n. So we need to select these n numbers from 1 to 2n, right? Now since we are doubling these numbers, it might be the case that some number exceeds 2n, becomes more than 2n. So first of all, we need to show that that does not happen. So my claim, okay, so we want to show that at the end of any iteration of this while loop, all the elements of this sequence must be at most 2n, right? And now initially this is true. Initially the sequence consists of the numbers 1 2 3 1 3 5 up to 2n minus 1, and all of them are less than equal to 2n. What do you mean by no, ascending back means I am just assigning si to double its value. So let's say si is equal to 3, so I am just now I am assigning si equal to 6. I mean, so by this I mean that instead of picking 3, I am picking 6 now. So initially I had these elements 1 2 3 4 up to 2n. So no, it's not a function. So what I'm saying is that initially I had these 2n elements 1 2 3 up to 2n. I picked n of them. So I picked the numbers 1 3 5 7 9 11 and so on. Now what I'm doing, suppose so now let's say we have 3, this element 3 dividing this element 9. Then what I am doing, I am just doubling 3, which what does that mean? That I am throwing 3 back and instead I am picking 6. Okay, so let's look at a concrete example. So let's say we have n is equal to 6. That is the numbers are 1 2 3 up to 12. So initially what did we do? Initially we started with all the odd numbers. That is, we started with 1 3 5 7 9 and 11. And now what are we doing? As long as, so we have picked 6 numbers, we need to pick 6 numbers, we have already picked 6 numbers. But now as we see that there are 2 numbers which divide each other, 3 divides 9. So in that case what I am doing is that I am doubling the smaller number, which means I am just dropping 3 and instead I am picking 6, right? So now my new sequence is 1 6 5 7 9 and 11, right? Now again, for example, this 1 is dividing all the other numbers. So what I am doing, I am just throwing away 1 and instead I am picking 2. So now my new sequence is this 2 6 5 7 9 11. Now again I see that 2 is dividing 6. So what I am doing, throwing away 2 and instead I am adding 4. So now my new sequence is 4 6 5 7 9 11. And now we see that in this sequence no number divides any other number. So this is a valid sequence that we want. Okay, is this clear? Okay, so that is what I am doing. I am starting with n numbers, which are the n odd numbers, and at each step, as long as we can find 2 numbers si and sj such that one divides the other, I am just doubling the smaller number, right? And I keep on doing this as long as some element of this sequence is divisible by some other element of the sequence. Okay. So now what I want to show as an invariant is that at the end of any iteration of this while loop, that is this doubling procedure, all the elements of this sequence are less than equal to 2n. That is, so from the description of this algorithm, it is not clear, since we are doubling some element, it might be the case that it exceeds 2n, but then we need to pick our n numbers from the set 1 2 3 up to 2n. So first of all we need to show that that does not happen. So at each time all the elements of this sequence are in fact less than equal to 2n. So initially this is true, because initially 1 3 5 up to 2n minus 1, all these numbers were less than equal to 2n. Now suppose up to some iteration it is true, right? Okay, so Okay, now what is happening in this iteration? We are just picking two elements Si and Sj, such that Si divides Sj, and we are replacing Si by 2 times Si. Okay, so now what we need to argue is that this 2 times Si is less than equal to 2n, right? Okay, now the thing is that, and initially we know that both these Si and Sj, both of them are less than equal to 2n. So we assumed this invariant was holding at the beginning of this iteration. So now Si and Sj, since Si divides Sj, which means that there must exist some number. So right, since Si divides Sj, there must exist some number more than 1, let's call it k, such that k times Si is Sj. And now k has to be greater than equal to 2. K cannot be 1 because Si and Sj are, so at any point, since initially the odd parts of these numbers were distinct, and now at every step what are we doing? We are just multiplying the numbers, we are just doubling the numbers. So the numbers cannot become equal because initially their odd parts were distinct, so then no two numbers can become equal at any stage, right? So hence this k has to be at least 2. But in that case, but in so then so even after multiplying this okay, so we have this, since k is at least 2, so we have 2 times Si less than equal to k times Si, but Sj was less than equal to 2n by our assumption. So which directly implies that 2 times Si is less than equal to 2n. So which means even after doubling, so now we are replacing Si with 2 times Si, but even after this step, this number is still at most 2n. So it does not exceed 2n, so hence we are picking all the numbers from the set 1 to 3 up to 2n. Okay, so hence the algorithm terminates. Now after the algorithm terminates, by definition, since the algorithm goes on along as long as we have two indices I and j such that Si divides Sj, so when can this terminate? When no element of when there are no such indices, which means no element of this sequence divides and any other element of the sequence. So this is what we want, this is what we were looking for. So when the algorithm terminates, we have this desired sequence. We have these n elements such that no element divides the other. Okay. Okay. So this is done. Any questions in this?
So it means Si is less than equal to n.
Sorry, yeah, Si less than equal to n, that is fine. Yeah, that we directly get from this. But what matters to us is 2 times Si is less than equal to 2n, because we are replacing Si with 2n, with 2 times Si, and what we want to show that even after this replacement, it's still less than equal to 2n. That is, this number is still picked from this set 1 to 3 up to 2n.
So how do we show that it is limited only up to n?
How do we show what?
That
Okay.
it is an n element subset without the property.
Yeah, so what was the cardinality of this set? So initially we started with how many elements? We started with n odd numbers, right? 1, 3, 5 up to 2n minus 1. These are n distinct odd numbers. And the cardinality of S does not decrease at every step. We are just doubling the elements. We are doubling some element at each time. So the number of elements in this sequence always remains n. Okay.
Yes.
Okay. So yeah. Okay. So if there are no more questions, we can go to the next problem. Okay. So what is this saying? That show that given any positive integer n, there is some integer k such that the digits of k times n are a sequence of ones and zeros. So what does this mean? That given any natural number n, there exists some multiple of n which consists only of ones and zeros, right? And we are talking about decimal numbers, it's not binary. So basically, given any number n, there is some multiple of n which consists only of ones and zeros. Okay, is the question clear?
Yes, sir.
Okay. Okay, so now how do we solve this? So if we want to apply pigeonhole principle, so which means we have to create some pigeons and we have to create some holes. So now if we want to get some number which is divisible by n, so we want to find a multiple of n which satisfies some properties. So now, which means in particular we want to find a number which is divisible by n. So in that case, what should we do? What should the holes correspond to? The holes should correspond to the possible remainders when a number is divided by n, right? So now if there are, so this is, I think all of you know this. So if there are two numbers a and b such that they leave the same remainder when divided by n, so in other words we can write it as this. So a congruent to b modulo n. So this notation means that both a and b leave the same remainder when divided by n. So in that case we know that n divides a minus b, right? So then, so if we want some multiple of n which satisfies some properties, so the holes are going to correspond to the remainders when some number, yeah, you can ask a question, go ahead.
Sir, if we have kn, both are natural numbers, so the product is also natural numbers,
Yes.
and uh, the sequence of, like, we won't have a decimal number, right? And even if we have, then it is like 1.00.
uh,
Again, a whole number itself.
1 point, no, k dot n is k into n, not decimal, I mean, so k is an this
Yeah,
is
yeah, k
multiplication.
into n. That
Yes,
is also a natural number, right? Because
yes,
both are
yes,
natural
yes.
numbers. So how can we say that the digits of that number are sequence of ones and
Okay,
zeros?
so let's consider an example. Let's say n is equal to 3. Okay, so now let's consider the number, let's say 1110. So this number it consists only of ones and zeros, and this number is divisible by 3, that you can easily check,
Yes.
right? So in this way, or let's say even you can take n equal to 37. 37 also divides this. So now we have to show this for any natural number. You need to show that for any natural number there exists a multiple of that natural number which consists only of ones and zeros. Okay.
So what does that bracket mean? We are talking about decimal numbers.
Oh, so I mean, do not confuse it with binary numbers. So I mean, you can ignore that. So I just mentioned it so that uh, we are not talking about binary numbers in any way. It's a sequence of ones and zeros. I mean, the decimal representation of the number consists only of ones and zeros. That's it. It's not like some binary representation. Okay. Okay. So then. Uh, So then what should be our holes in this case? Our holes should be the possible remainders when some number is divided by n. Because so then if two numbers belong to the same whole, that is if two numbers a and b leave the same remainder when divided by n, in that case we can say that the difference of those two numbers must also be divisible by n. Right? I think this everyone knows, right? If two numbers have the same remainder, then their difference must be divisible by n. Okay, so then, so in this case our holes by n, right? And so what are the possible remainders when some number is divided by n? It is this, right? So these are the possible remainders when some number is divided by n. So then what we want, so these are our holes, we have n many holes. So what do we want? We want to find some n plus 1 many numbers such that, so if we have any n plus 1 many numbers, we know that there are two numbers which have the same remainder. So what we want is that the difference of those two numbers must consist of only ones and zeros. So we want to construct n plus 1 numbers in such a way that the difference of any two numbers consists only of ones and zeros. In that case we are done, right? So let's consider this case. So consider the numbers So consider these numbers. So 1, 11, then 1, 1, 1 and so on. So the n plus, so the ith number consists of I consecutive ones. So we have these n plus 1 numbers. Okay. So now if we divide these n plus 1 numbers by n, the remainders, there are n possible remainders, which are this 0, 1, 2 up to n minus 1. So then we must have, by PHP, by pigeonhole principle, there must be two numbers such that they have the same remainder. So right, so consider these two numbers. So if we subtract the larger number from the smaller number, so what are these numbers like? So the larger number consists of a larger number of ones. So this is my larger number. So if we subtract the smaller number just consists of a smaller number of ones. So it's something like this. So if we subtract this, what will we get? We'll have some sequence of ones followed by some sequence of zeros, right? And this number is divisible by n because both of them have the same remainder. So their difference is divisible by n, and the difference consists of a sequence of ones and zeros only, right? So okay. Okay, is this clear? Okay, so if there are no questions, we can go to the next question. Okay, so what does this say? That let a1 up to an be a sequence of positive integers. We need to show that for some two indices I and j, where I less than equal to j, the sum, if we take the sum from ai plus 1, ai plus 2 up to aj, that is divisible by n. So what is it saying? That so we have the sequence of numbers a1, a2, a3, a4 and so on up to an. So what is it saying is that there will exist two indices, let's call it I and j, such that this sum, the sum of the elements from ai to aj, this sum will be divisible by n. So there is some contiguous subsequence whose sum is divisible by n. That is what we want to show. Okay, is the question clear? Okay, so again, if we want, as in the previous problem, if we want to show that some number is divisible by n, again, what should be my holes? My holes should again be the possible remainders when some number is divided by n. So again, these are my possible holes. There are n possible holes, right? Now, what do we need to do? We need to construct a set of numbers, that will go into these holes, and we need to show that at least two of them must go to the same hole, and then their difference will be divisible by n. That is our approach. Okay, so let's consider this sequence. Okay, so let's consider these n numbers. So Si is just the sum of the first I numbers in this sequence. It is the prefix sum of the first I numbers. Okay, so now if any of these n, so there are n numbers, if any of these n numbers is divisible by n, we are done, right? We need to so we wanted to show that there is some contiguous sequence whose sum is divisible by n. So now if any of these SIs is divisible by n, we are done, because we have already got a sum that a1 plus a2 plus up to ai is divisible by n. So okay, so suppose this is not the case. Suppose that none of these SIs is divisible by n, right? So then if we divide these SIs by n, what are the possible remainders? It has to be in this set 1, 2, 3 up to n minus 1. It cannot be 0, right? Because none of these numbers is divisible by n, so the remainder cannot be 0. It has to lie in this set. But now how many elements are in this set? There are n minus 1 many elements in this set, or basically we have n minus 1 holes now. Okay, so now we have n numbers, n pigeons, s1 up to sn, and we have these n minus 1 holes. So then at least two of them must go to the same hole. So
what is the condition? Why it is not 0?
so if it is 0, so suppose, let's say, suppose Si is divisible by n. Okay, if so, that is the remainder is 0. When n divides Si, the remainder is 0. So in that case, what do we have? That a1 plus a2 plus up to ai, this sum is divisible by n, and we are already done, right? We needed to show that there exists a contiguous sequence, contiguous subsequence whose sum is divisible by n, and we have already got that. So here basically our I is 1 and j is I. I mean, you get it, right? So this is my ai and this is my aj. So this sequence, the sum of this sequence is already divisible by n, and we are done. So we need to consider the case when this is not the case. So none of these SIs is divisible by n. So in that case, what are the possible remainders? It has to be some element in this set 1, 2, 3 up to n minus 1. Okay, is it clear?
Yes.
Okay. So then we have n numbers s1 up to sn and n minus 1 possible remainders, which means that two of these numbers must have the same remainder. So Okay, so then and so then their difference, that is Sj minus Si, is divisible by n, since both of them have the same remainder. So but now what is Sj minus Si? It is just this thing, right? Sj is like you take the sum from a1 plus a2 plus up to aj, and Si is like a1 plus a2 plus up to ai. So if you take their difference, we are just left with ai plus 1, ai plus 2 up to aj. So this is a contiguous subsequence. So we are done. So this is a contiguous subsequence whose sum is divisible by n. Okay.
Sir, I didn't get. How do
Yes.
you say that there exists such i's and j, the I and j
So
which have
this is
same
by
remainder?
pigeonhole principle. So okay. So now we have n pigeons. So my pigeons are these SIs. So this S1, S2 up to Sn. These are my pigeons. Okay. And my holes are this. We have n minus 1 holes. These are the remainders when these SIs are divided by n. Okay, because we assume that n does not divide any of them, because if n divides any one of them, we are done. So we assume that n does not divide any of them. So in that case, the possible remainders are 0 is not a possible remainder. So there are n minus 1 possible remainders, and we have n possible numbers, n numbers here. So 2 of them must have the same remainder. So that means we have Si and Sj having the same remainder, and then their difference must be divisible by n. Okay. Okay. So this is done. Okay. So now let's look at the next question. So this says that if we have n plus 1 integers chosen from 1 to 3 up to 2n, so by box of 3n I mean the set 1 to 3 up to 2n, then we need to show that there are always two numbers which differ by at most 2. So which means we have the numbers 1 to 3 up to 3n. Out of these 3n numbers, we choose any n plus 1 integers, and we need to show that no matter how we choose these n plus 1 numbers, there will always be two numbers in this chosen set which differ by at most 2, whose difference is at most 2. Okay, is the question clear? Okay. So this problem we are going to solve using contradiction. So assume it is not the case. That is, out of these n plus 1 numbers, no two numbers, the difference of no two numbers is at most 2. So okay, so we assume for a contradiction, we assume that the difference of any two numbers is at least 3. Okay, so what we do, we arrange these chosen numbers in ascending order. So let's say okay, so let's say these n plus 1 numbers arranged in ascending order, we are calling it as x1 x2 up to xn plus 1. Okay, so then what do we have? X1, it is surely at least 1, obviously, because these numbers are chosen from 1 to 3n, it's obviously at least 1. Now x2, this has to be at least x1 plus 3. By our assumption, we assume that the difference of any two numbers is at least 3, so x2 has to be at least x1 plus 3. So this is at least 4, because x1 is at least 1. Similarly, x3, this has to be at least x2 plus 3, which is at least 7. 4 plus 3 is 7. And we can continue like this. So if you notice, so what is this? 1 is basically 3 into 0 plus 1. This is 3 into 1 plus 1. This is 3 into 2 plus 1. Okay, so if we continue like this, then what will we get? That xn plus 1, this will be at least xn plus 3, and then by the same approach, this is going to be 3n plus 1. Right, by this thing we can say that continuing like this, xn plus 1 has to be at least 3n plus 1, which is a contradiction, because we assume that all these numbers were chosen from 1 to 3 up to 3n. Okay, okay, this was pretty simple, I think. Are there any questions?
No, sir. Everything is clear.
Okay, okay, so let's go to the next problem. So this says that given any set of 52 integers, there exists two integers whose sum or whose difference is divisible by 100. So we are given 52 arbitrary integers. We need to show that there will always exist two integers such that either their sum or their difference is divisible by 100. Okay, so till now what we were looking at was only differences. So we were trying to find out numbers whose difference, which had the same remainders, and then their difference was divisible by some number. But now in this case we also need to consider the sum. So we need to create our wholes in such a way that we can incorporate both the sum and the difference. Okay, so now so let's say we create our wholes in this way. So depending on the possible remainders, right? So when some number is divided by 100, the possible remainders are this. So now there are 100 possible remainders. So intuitively we have 100 wholes, but then we cannot apply pigeonhole principle, right? Because we have only 52 many pigeons, 52 integers, and so the number of wholes must be at most 51. Then only we can apply pigeonhole principle. So in some way we need to reduce the number of wholes. So what do we do is that we group these wholes so that the number of wholes reduces. So let's say suppose we group the wholes in this way. That is, if the remainder, if some, when some number is divided by 100, if the remainder is 0, we put it in this hole. If the remainder is either 1 or 99, then we put it in this hole. If the remainder is either 2 or 98, we put it in this hole, and so on. Finally, if the remainder is 50, we put it in this hole. Okay, so this is how we create the wholes. So depending on the remainder, so if the remainder is either 0 or 50, we put it into the respective holes. Otherwise, if the remainder is either 1 or 99, we put it in this hole. If it is either 2 or 98, put it in this hole, and so on. Okay, so then what is the number of holes? So you can easily see the number of holes is 51. Okay, the number of holes is 51. So then, since we have 52 integers, so at least 2 of those integers must belong to the same hole. Okay. So now if this same whole, if it is either 0 or 50, then what do we know? That both these numbers have the same remainder when divided by 100, which is either 0 or 50. In that case, their difference will be divisible by 100 and we are done. So okay. So now the only case we need to consider is when these two numbers go to some non-trivial whole. That is, so otherwise, okay. So otherwise the whole is of the form r comma 100 minus r for some integer r. Okay, so which means that both these numbers, both these numbers when divided by 100, their remainder lies in this set. It's either r or it is 100 minus r. Now if both the remainders are r, or if both the remainders are 100 minus r, then again we do the same thing, that is their difference is divisible by 100. So right, so then the only case to consider is when one of them has remainder r and the other number has remainder 100 minus r. So in that case what we want to say is that the sum of these two numbers will be divisible by 100. Okay, otherwise, so the only case we need to consider is so right, so these two numbers a and b, these were the numbers. So these were the numbers. So one of them, let's say a, leaves remainder r and the other number b leaves remainder 100 minus r. Okay, but in that case their sum a plus b, this will be okay. Okay, so here the technique was to reduce the number of holes. Intuitively we have 100 different holes, but since the number of integers is less, the number of pigeons is less, so we need to group the holes so that the number of holes reduces. Okay, is this clear?
Difference is also divisible by 100. Yeah?
Sorry?
A minus B is also divisible by 100
No,
in
so
this case.
if we do a minus b, there will be a 2r coming, no? So let's say we do a minus b, this is going to be 100 times q1 minus q2 minus 100 plus 2r. So this 2r might not be divisible by 100 because r is some number in like 1 to 49. So this 2 times r, it is surely not divisible by 100. Right?
Yes, sir.
Yeah. Okay. Okay, so let's go to the next question. So this says that suppose we are given 10 persons whose age is a whole number between 1 and 60. So there are 10 persons, and their ages are between 1 and 60. So we need to show that one can find two groups of people, disjoint groups of people, having the sum of their ages equal. That is, so let's say the persons are So let's say the persons are P1, P2 up to P10, and all of their ages lie in the range 1 to 60. So what we need to show is that there will exist two disjoint subsets of this. So let's say maybe one subset may consist of P2 and P3, and the other may consist of P5, P6 and P10. So there will always exist two disjoint subsets of people such that their sum of ages will be equal. Okay, is the question clear? Okay. So now, how many, so there are 10 people, how many possible distinct subsets of people are there? So, since there are 10 people, the number of distinct non-empty subsets, it is 2 to the power 10 minus 1, which is like 1023. Right? This is the number of distinct non-empty subsets of people. Now, consider any such subset. What is the maximum possible sum of ages of, so
120.
Why 120? Sorry. Yes. So
Sorry, there will be 10 people in one group and
Yes.
another group in 10, and if all are 60 years old, then
yes,
600.
600. Right, so this is the maximum possible. So which means, so consider any subset of people, their sum of ages must lie, so right, this is obvious then. So if you consider any subset of people, their sum of ages must be some natural number between 1 and 600. Okay, so now it's very simple. So there are 1023 possible subsets of people and only 600 possible sums. So by trivially using pigeonhole principle, there will exist two distinct subsets which have the same sum. So sum of ages starts from 10. No. So there are 10 persons and each of them has age between 1 and 60. So a person's age can be 1.
So 10 times 1 is 10. So
Yes.
minimum age of
Okay. Yeah,
some of-
that will even, but no, but so I am considering, so a subset has at most 10 people, but a subset may have lesser number of people. For example, in the example which I showed, we were just considering P2 and P3. So a subset maybe consists of a single person whose age is 1. Right, so we are not considering subsets of size 10, we are considering any subset, any non-empty subset which might consist of just a single person and his age may be 1. So therefore I am considering any subset, the sum of the ages, it is, so
but if we have, the question says given 10 people
yes,
between this age group.
yeah,
So, okay, other than empty set, we have to form any other subset.
yes. So we need to show this thing, no, that we can find two groups of people, disjoint groups of people whose sum of ages is equal. So these two subsets, they have to be disjoint. So we do not know the cardinality of these two subsets. Okay, how do I
Okay.
increase the screen size? Okay, is the screen size fine now? I don't know. I don't think I can increase beyond this. Okay. So there will exist two distinct subsets having the same sum. Right? But now these two subsets, they may not be disjoint. They are distinct subsets. Okay, how do I zoom in? Okay, fine. Yeah. Okay. So now what we have got is we have got two distinct subsets. Okay, so like you all can increase the screen size for yourself, no? I think that is yeah, because since I'm sharing the screen, I think you can increase the screen size for yourself. Okay. So what we okay, so is there any fix? How can I do something? Uh, I don't think I can do anything other than this. Screen orientation. So how do I change the screen orientation? Okay. So but the size I think remains the same, isn't it? Or is this fine, or is this size fine? Okay. Okay, I think as long as you can, so it's you can read you can read what I'm writing, right? So I'll try to fix it from the next session, but as long as you can read, I think it's fine. No? Okay. Okay. So yeah, so what we have got is we have got two distinct subsets which have the same sum. But note that these two subsets, they are distinct but they may not be disjoint. So for example, it might be the case that these two subsets are, let's say, P1, P2, P4 and P5, and the other subset consists of P2, P4, P6 and P7. So we have got two subsets whose sum of ages are same, but they are distinct. So this subset is distinct from this subset, but they are not disjoint. They may have common entries. So for example, P2 and P4 might be common, but in that case, just delete the common people. Even after deleting the common people, the remaining what okay, so Shashikant, can you read what I am writing? I'll try to do this from the next session, but for this session, it will take a lot of time. I think if I try to do all these things. So maybe I'll surely fix this from the next session. Okay. Yeah. So yeah. Okay. So yeah, so we just delete the common persons from these two subsets. So these are two distinct subsets, but they may have common persons. So just delete the common persons. So even after deleting the common persons, we have here P1 and P5, and here we have P6 and P7. So their sums must also be equal. Since sum of this subset was equal to sum of this subset, even after deleting the common persons, still their sums, the remaining sums must be equal. And so we are done. So we have got two disjoint subsets of people whose sum is same. Okay. That's it. So we are done. So we have got two disjoint subsets of people whose sum of ages is the same. Okay, so is this clear?
Yes, sir.
Okay. Okay. Now the next question is on Ramsey numbers. So I think sir covered a bit of Ramsey numbers, but he left one basic question as a open thing. So the first thing is, what is a Ramsey number? The Ramsey number Rmn, it is the minimum positive integer, let's call it P, such that any graph on at least P vertices. So suppose we have a complete graph on P vertices and we color the edges arbitrarily with two colors, let's say blue and red. So either there will be a complete subgraph all of whose edges are blue, or there will be a complete subgraph all of whose edges are red. Right? So if we look at that, so what is Rmn? So I've written it already here. So Rmn is the minimum positive integer such that any red blue coloring of the edges of Kp, so Kp means the complete graph on P vertices. So if we take any complete graph on P vertices where P is more than some threshold, which is the Ramsey number, then any red blue coloring of the edges must contain a copy of Km, which is a complete graph on M vertices, all of whose edges are blue, or a complete graph on N vertices, all of whose edges are red. Right? So it is the minimum integer such that any graph on at least those many vertices will have this property, that if we color the edges arbitrarily with two colors, either there will exist a complete blue graph on M vertices, or there will exist a complete red graph on N vertices. So the minimum such integer is called Rmn. But now the fundamental question is, why should such a number exist? Like, why should we have some such value of P such that any graph on at least P vertices has this property? This is a fundamental question. So let's look at a proof of this. Why should the Ramsey number exist? Okay, so we are going to prove this by induction. So we are going to do induction on M plus N. Okay, so now M and N both are natural numbers. Okay, so do you know definition? Okay, so do you know definition of graph? Like what is a graph? So a graph is basically a set of vertices and a set of edges, right? So you don't need to know much about graph theory for this. You just need to know that so what is Km? Km is the complete graph on M vertices. That is, we have M vertices and all these edges are there. For every pair of vertices there is an edge. So this is the, so for example, this is the complete graph on 6 vertices. So I may have missed some edges, but you understand. So Km is basically, you have M vertices and between every pair of vertices there is an edge. Okay, now what we are doing here is we are saying that given any integers M and N, there exists a threshold, let's call it P. There will exist some integer P which is a function of M and N, such that now you consider Kp, that is you consider the complete graph on p vertices on you consider any graph on at least p vertices. So K, let's call it KL, where L is greater than equal to p. So you consider the complete graph on L vertices. So all these edges are there. Now what are you doing is you are coloring. So how many edges are, since there are L vertices, there are L choose to many edges, right? Because between every pair of vertices there is an edge. Now what are you doing? So we are coloring all these L choose to edges arbitrarily using two colors, red and blue. So each edge we are arbitrarily coloring with red or blue. Okay, so now what this Ramsey's theorem says is that any graph on at least p vertices, so no matter how you color this, you will always be able to get either m vertices such that all these edges are blue, or you will be able to get n vertices such that all these edges are red. For example, let's consider a smaller example. Let's consider, suppose we want to find the value of R33. So what does this mean? So my claim is that R33 is equal to 6. So what do we mean to say? That if we have any graph on 6 vertices, so if we have any complete graph on at least 6 vertices and we color all the edges using two colors, red and blue, either we will be able to get a blue triangle or a red triangle. Okay, so let's consider any graph on 6 vertices. Let's look at a proof of this. This is a very simple proof. Okay, so we have 6 vertices. Okay, now all the 6 choose to edges are there, and what are we doing is we are coloring these 6 choose to edges with two colors, red and blue. And what do we want? We want to show that no matter how we color these edges, we will always be able to find a K3. K3 is just a triangle, right? 3 vertices, it's just a triangle. So we will be able to find either a triangle which is blue in color or another K3, that is another triangle, such that all these edges are red in color. So let's try to prove this. Suppose, consider this vertex, right? Consider this vertex. So now consider these 5 edges. So this vertex has 5 edges incident on it. So out of these 5 edges, since we are coloring with two colors, that is red and blue, so then we know that at least, so there must be at least 3 edges which receive the same color by pigeonhole principle. So there are 2 holes and there are 5 pigeons, so at least there must be 3 edges which receive the same color. So let's say there are 3 edges which receive blue color without loss of generality. So let's say, so suppose that okay, so suppose that these 3 edges receive blue color. So now consider this edge. So if this edge had blue color, then we are done. Then we have already obtained a blue triangle. We have already obtained 3 edges, like a K3. So this is my K3, such that all of its edges are blue. In this case we are done. So suppose it is not the case, then in that case this edge must have been colored red. Okay, similarly this edge must also be colored red, otherwise you would have got a blue triangle here in this case. Okay, now consider this particular edge. So if this edge was blue, this green dotted line, if this edge was blue, then we have a, then we already have a blue triangle, this triangle, right? Otherwise, if this green edge was red, in this case we have a red triangle, this. Okay, so what we have shown, that if we have any graph, any complete graph on at least 6 vertices, and we color the edges of this graph arbitrarily with red or blue, either we will have a red triangle or a blue triangle. Okay, so this we can generalize to any two integers m and n. So in general, if we have any two integers m and n, we want to say that there exists a p. So in this case, my p was equal to 6, such that if we color the edges of the complete graph on p vertices, so we have this complete graph on p vertices, and we color the edges arbitrarily with two colors, okay, red or blue, then we want to say that no matter how we color, we will always be able to get either a blue complete graph on m vertices or a red complete graph on n vertices. Okay, this is the definition of Ramsey number. So Ramsey number is the minimum possible value of the number of vertices in such a graph. Okay, is the definition of Ramsey number clear? Okay, but now the fundamental question is, okay, so for when m equal to n equal to 3, we saw that 6 vertices suffice. But now the question is, yeah, okay, but now the question is, for general m and n, for any two arbitrary integers m and n, why should such a value exist at all? Like we are telling, yeah, so we are telling that, so Ramsey number m comma n is the minimum value of p such that any graph on at least p vertices will satisfy this property. But the question is, why should such a p exist? So that is what we want to prove. And this we are going to prove by induction on m plus n, on the value of m plus n. Okay, so now since m and n both are natural numbers, so m plus n is at least 2, and that is the base case. So when m plus n is equal to 2, so this can only happen when m is equal to 1 and n is equal to 1. So then my claim is that r1 comma 1, this is just equal to 1. And why? Because suppose we have just one vertex in a graph, there are no edges, so the coloring is, we don't need any coloring. And this condition, so what is the condition we need? That either there will exist a complete graph on one vertex, all of whose edges are red, but there are no edges, or there will exist a complete graph on one vertex, all of whose edges are blue, but there are no edges. So this statement is vacuously true, right? So this one vertex, it's itself a complete graph on one vertex which does not have an edge, does not have any edge. So this condition is vacuously true. So r1 comma 1 is 1, but yeah, so which means r1 comma 1 exists. That is all that we care for. Okay, so now we want to show, so assume that, so suppose we want to show that r of m plus 1 comma n plus 1 exists. Right, so here the value of the sum of these two parameters is m plus n plus 2. So we can assume, by strong induction we can assume that so okay, okay, so let us say for any RNS whose sum is at most m plus n plus 1, the Ramsey number r comma s exists. And now we want to show that when this sum of these parameters is m plus n plus 2, this also exists. So we want to show that r of m plus 1 comma n plus 1 exists. Okay, okay, so how do we show this? So my claim is that I want to show this. So what do we do? Consider any graph on, so let's say we set p is equal to this quantity. Okay, so let's say we set p is equal to this quantity and consider any graph on p vertices. Okay, so consider Okay, so we consider the complete graph on P vertices and we color its edges arbitrarily with blue or red. Okay, so let's consider any vertex of this graph, complete graph on P vertices. So now the edges incident on this vertex, all of them are colored either blue or red. So let us group the vertices based on the color. So here we have a set of vertices such that these edges are blue in color, and here we have a set of vertices such that these edges are red in color. Okay, so we just consider any vertex and partition the remaining vertices based on the color of their incident edge from this vertex V. Okay, so let us call this set to be A and this set to be B. Fine. So then my claim is that either so the claim is that either the size of A is at least this or the size of B is at least this. So one of these two conditions must hold. And this is very simple. So if both these conditions do not hold, then what will happen? So if not, then the number of vertices in the graph will be at most what? So if mod A is less than this, so which means mod A is less than or equal to this. So if the size of A is not at least this, which means it is less than or equal to R of m comma n plus 1 minus 1. Similarly, the size of B is at most and this plus 1 is for the vertex V. Right. So if both these conditions fail, that if mod A is not more than R of m comma n plus 1, which means the size of A is at most this. Similarly, if the size of B is not more than this, which means the size of B is at most this, and there is one vertex V here which is plus 1. So then what is this equal to? Minus 1, right? So one of these minus 1 cancels out, but there is still a minus 1. But then we assume that this graph consists of this many number of vertices. P is equal to this. But if both of these conditions fail, then we have that the number of vertices is at most this thing minus 1, which is a contradiction. Right? So at least one of these two things must hold. Either the size of A is large or the size of B is large. One of these conditions must hold. So we consider both these cases separately. So case 1, okay. So in this case, if the size of A is large, so by definition, what is R of m comma n plus 1? So the size of this set is at least R of m comma n plus 1, which means that, and the edges of this are arbitrarily colored with blue or red, which means that by definition either there will be a blue colored complete graph on m vertices, or there will be a red colored complete graph on n plus 1 vertices by definition. So either either there is a blue complete graph on m vertices or there is a red complete graph on n plus 1 vertices. Now if this is the case, then we are done. right? If there is already a red colored n plus 1 vertices, red complete graph on n plus 1 vertices, then we are done, right? We recall what did we want to show. We wanted to show that r of m plus 1 comma n plus 1 is upper bounded by this, which means that we need to show that any graph on this many number of vertices will either have a blue colored complete graph on m plus 1 vertices or a red colored complete graph on n plus 1 vertices. That is what we needed to show. So if there is already a red colored complete graph on n plus 1 vertices, we are done. Otherwise, if there is a complete graph on m vertices which is colored blue, then combining it with v, right? So here we have m vertices such that all these edges are blue. So if we include v in this, since all these edges are blue in color, we will have a complete graph on m plus 1 vertices, all of whose edges are colored blue, right? So in this case we are done, and in this case we include v. Right, so in this case also we are done. Okay, so in case 1 is complete. So next, in case 2, we have this. So now what does this say? The size of this vertex set is at least r of m plus 1 comma n, which means that either there is a blue complete graph on m plus 1 vertices or there is a red complete graph on n vertices. And again we do the same thing. If there is already a blue complete graph on m plus 1 vertices, we are done. And if there is a red complete graph on n vertices, then we include v with this, with all these red edges, and we are done. So it's exactly similar, just the opposite thing. So this is right. So hence by induction we showed that r of m plus 1 comma n plus 1 exists. That is, we have shown an upper bound, and that is all we need. We have shown that any graph on at least this many number of vertices will satisfy this property that we want. Either there is a blue complete graph on m plus 1 vertices or a red complete graph on n plus 1 vertices. So hence Rmn exists. We have shown by induction. Okay. So any doubts in this? Okay, so if not, we can move to the next question. So the remaining two questions are from the assignment. So in the assignment 1 there are 4 questions, out of which I think you have to submit 2 of them, the question 2 and 4, and the remaining 2 are for practice. So I'm going to cover the practice questions. Okay, so the first question is, prove that the decimal representation of a by b, where a and b are co-prime numbers, has period of repetition less than or equal to b minus 1. So what does this say? That here a and b are two co-prime integers, which means that GCD is equal to 1. So a by b is a rational number, so we can have a decimal representation of it, and that may not be a finite decimal. So for example, 1 by 3, this is equal to 0.3333 and so on, right? But it can also be a finite decimal. So what we need to show, so here what is the period of repetition? It is just 1. 3 is repeating infinitely, right? Or we can have some decimal, let's say for example 0.212121 and so on. So for this decimal, the period of repetition is equal to 2, right? So what we need to show is that for any two integers a and b whose GCD is equal to 1, if we write down the decimal representation, the period has to be less than or equal to b minus 1. Okay, is the question clear?
What about where it terminates at say 1 by 2 as 0.5.
Yeah, so then the period of repetition is, so let's say we have 0.5, the period of repetition is 0, there is no repetition.
Yes.
Yeah, so in that case, if it is a finite decimal, its period of repetition is 0. Okay. So now, first of all, we can assume without loss of generality that A is less than B. So let's say, so let's say when A is divided by B, the quotient is Q and the remainder is R. Okay, but then what is A by B? It is equal to Q plus R by B, and here that this is a unique representation of this is a unique that there is a unique quotient and remainder when A is divided by B, and the remainder has to be less than B. So A by B is just Q plus R by B. So R by B, this quantity is less than 1, is a decimal. So here Q is the integer part, and R by B is the decimal part. So if we write the decimal representation, it is going to be Q. So Q is some number, point something, this something is basically R by B. Right? So we do not need to worry about Q, we just need to worry about the part which is after the decimal. So that is, we need to worry about R by B. Okay, so hence without loss of generality, we assume that A is less than B, because otherwise instead of working with A, we work with R. Fine. Okay.
So R by B lies between 0 and 1.
Yes. So R by B lies between 0 and 1. So hence A is less than or equal to B. Otherwise we just work with R. Okay. So now imagine that we are performing the long division. We suppose we are just dividing A by B. So what are we doing? So we have B here, we are dividing. So the first we have a decimal, since A is less than B, so first we have a decimal point. So we put 0 here, and then we have some number in the quotient. So then we will get some number here, and there will be some remainder. And again what we do, because of this decimal, we will put another 0, we will have some number in the quotient, we will have something here, and there will be some remainder. So let's call this R1, this R2. Then again we will put 0, and we are going to continue like this. Right? Now the thing is that if at any point this Ri, it becomes 0, then there is no repetition, right? If this remainder at any point becomes 0, then the period of repetition is 0. Okay, so that is the first thing. So okay, so let the sequence of remainders obtained in this way be R1, R2, R3 and so on. So if at any point Ri is 0, then the decimal is finite and there is no period of repetition. So for example, if we have half, then half is equal to 0.5, and after this the remainder will be 0. Right? So when we are dividing 1 by 2, first we will have a point, then 10, and remainder is 0. So in this case we are done. The period of repetition is 0, and which is at most b minus 1. So here we are done. So otherwise assume that none of these Ri's is 0. But in this case, what are the possible values of Ri? So recall that what is Ri? So Ri is the remainder when this number a appended with 0 is divided by b. Right? So a and then 0, this is a decimal number. So when this number is divided by b, what is the remainder? That is R1. So obviously all these Ri's have to be less than or equal to b minus 1. The remainder when some number is divided by b has to be less than or equal to b minus 1. So, and also it is not 0 we assumed. Right? So then all these Ri's, they lie in this set 1, 2, 3 up to b minus 1. Now if at any point this Ri repeats, so let's say, so during division, so here initially R1 is coming, then again when we append 0 to R1, R2 is coming, and then once we append 0 to R2, again there is R1. In this case, we can forever continue like this. We can say that the sequence of remainders will be R1, R2, R1, R2 and so on, right? Because when once some remainder repeats, so then the next sequence of remainders have to be the same, because the same thing is going to repeat, right? Is this clear? So for example, let's say when we had let's consider some example. What? Suppose we consider this. We are dividing 1 by 7. So we have so it's going to continue for some time, 50, but then we have yeah, so okay, this part is a bit messy, but you can see. So for example, we start with this. So first we divide 10 by 7, the remainder is 3, right? Again we append 0, we divide 30 by 7, the remainder is 2. Again we divide 20 by 7, the remainder is 6, and so on. We have 4, then 5, and then again 1. But now once we have this 1 here, again, so since initially it was 1, so again the same sequence is going to repeat. So again the next sequence of remainders have to be 3, 2, 6, 4, 5, 1. Again the same sequence is going to repeat, right? So once this Ri, once we have the same Ri, the same sequence is going to repeat. Okay? Okay. So which means initially how many terms can there be? So when we are so let's write this. Okay. So let's consider the first time when R1 repeats. So when we are dividing A by B, we have 0. So we are looking at the quotient. So we have 0 point something, and the corresponding remainder is R1. Then we have something, the corresponding remainder is R2, and so on. So finally, once R1 repeats, these quotients, these terms are also going to repeat by the exact same logic. So the first time when R1 repeats, we will have a repetition. So that is the period of repetition. But then what can be the maximum time after which R1 can repeat? There can be at most b minus 1 possible values, because all these Ri's lie in the must be from this set 1, 2, 3 up to b minus 1. So after at most b minus 1 things, R1 must repeat. So here we must have at most b minus 1 possible values.
But
right?
that is the value of what the remainder takes and not the number of times we have the remainder, right?
uh, so okay, so initially, so if we look at, okay, let me write that example again. So initially we start, sorry, okay, so my first term in the quotient that is here is going to be 1. Then my first remainder is 3, so this is my r1. Then so next term is 4, so here it is 4. Then my r2 is equal to 2. Okay, so r1 is 3, r2 is equal to 2, but then again, okay, so here we have 2, and then r3 is equal to 6. So 8, and here we have 4. Okay, so 1, sorry, 7. Okay, so here in the quotient we have 0.142857, but then this remainder is repeating. So initially we had 10, and now again we have 10. So then what will be the next term in the quotient? It has to be again the same thing. Again, it after this, again it has to be the same sequence. It has to be 142857, again 142857, and so on. Right, once this quotient becomes same, once this divisor becomes the same, the sequence of quotients here must also be the same. Right, is it clear? So yeah, but then what can be the maximum possible number of such distinct things? It can only be b minus 1, because these remainders, there are at most b minus 1 possible values. Okay, so then after at most b minus 1 terms, we must have a repetition. So therefore we are getting
Here our B is 7 and
yes,
A is 1, right?
a is 1, yes.
So we did get a value of R is equal to B, that is 7, because 7 sevens are 49.
No. So this is the quotient. This can be anything between 0 and 9. But
Oh, okay.
the remainder. So see the remainder sequence. So what is the sequence of remainders here? So 3, then 2, and 6. These terms has to be less than 7, strictly less than 7,
Yes.
right? Because we are dividing by 7, so remainder has to be less than 7. So yeah. So this, for example, is an example where we actually the period of repetition is actually 6. After 6 terms, we are getting a repetition. So that means
I got that the remainder should be less than 7, but not why the repetition also has to be less than 7.
okay. So which means, so here, okay, initially it was 1, then it became 3, then it became 2, then 6, 4, then 5. After this, we again have 1. But once this 1 comes, so this entire thing which happened here, again the same thing is going to repeat here, right? And if the same thing is
Yes.
okay, so because, sorry, what is this? So because once we have 10 here, the same thing which happened initially, the same thing is going to repeat forever. And in that case, the quotient also must follow the same sequence as, so when 10 was here, the first term was 1. So again after this we must have 1, and right, the same thing must follow. So did you understand?
Yes, I got that, but I didn't. So suppose I have
Yes.
1, 3,
Yes.
2, 6,
Oh,
4, 5,
yes.
and
So after this we,
I cannot have 0 or 7.
yeah, because if we had 0, then the period of repetition is 0. It's a finite thing. So
Yes.
yeah, and the first time when it repeats, it must repeat the same sequence again and again forever. So then the number of possible distinct remainders is b minus 1. So the period of repetition can also be at most b minus 1.
Yes.
Yes. Okay.
So, by the way, what is the like importance of A and B being co-prime?
Uh,
There any significance?
so thing is that yeah, it's not actually required. So because we assume that wait, yeah, it's not wait.
Because I don't see like 1 and
Hmm.
10 or 1 and 7 being co-prime, right? Because one can divide both of them, 1 and 7
Oh
both.
yes, yes, yes. It's not required. Yeah. So basically, yeah, it's not required. I mean, so if it is not co-prime, you can make it co-prime by dividing with a common factor. That is the thing. But yeah, it's not
Uh,
required. Yeah.
right. For example, like even 1 by 7 or 2 by 14 will give the same
Yes, yes, yes.
repeating
Yeah,
sequences.
yeah. Exactly. Yeah. 1/7 and 2/14 is the same thing. So it's okay to consider just GCT1 without loss of generality. But yeah, in the proof, it is not required. Yeah.
Okay. What if the GCD is not 1? Will that make a difference?
No, no. So as you said, for example, if the GCD is not 1, then just
Right.
divide by the common factor and then do this argument. That's the thing.
Uh,
Or even
a,
anywhere in this argument, we never use the fact that the GCD is 1. So it's not a problem.
okay.
So
So
even if
okay.
there was, let's say, 14 and 2, it would have been the same thing.
So like this will be always true for all natural numbers A and B,
Yes,
right?
yes, yes. Yeah, that is what we showed. Yes.
Okay.
Yeah. Okay. 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 So now let's look at the last question. Okay. So here we consider the Fibonacci sequence. So I think most of you must be familiar with this Fibonacci sequence. So the first two terms of this sequence are 1, and then each subsequent term is the sum of the previous two terms. Okay. So the first question says that for any positive integer m, we need to show that this sequence bi, which is the remainders modulo m. So we have this Fibonacci sequence, and each term we divide by m and take the remainder. So this sequence is periodic. Okay. So for example, let's write down the sequence of few terms. So the first two terms are 1, then it's 2, 3, 5, 8. And so on. I think it's fine. Yes. Okay. So now let's say we take the, so let's say m is equal to, let's say 6. So if we take the remainders with respect to 6 of these sequence, then what do we get? 1, 1, 2, 3, 5. Then when 8 is divided by 6, remainder is 2. Then we have 1. Then what do we have? 3. Then 4. Okay, so we need to keep going for some time. So then we have 89. So yeah, it's going to be some sequence, but the thing is that we have to show that after a point this has to repeat. So it cannot be some arbitrary sequence. So we can try going for some time. Then uh, 10. Yeah, so I mean, this is probably the period of repetition can be large, but the thing is that we have to show that this sequence is periodic. So I mean, so it starts with one and then something, and then it must repeat. That is what we want to show. So this sequence is the same as this sequence, is the same as this sequence, and so on. Fine, is the question clear? So it may be large, the period of repetition may be large. That is why we are not being able to find in such a small range. But if we take sufficiently large sequences, then it will repeat. The sequence of remainders must repeat. Okay, is the question clear? So for any natural number m, we need to show that this sequence of remainders must repeat. Okay, so how do we show this? Okay, so let's consider pairs of remainders. So for any two consecutive term in this remainder sequence, we consider the pair. Okay, okay, so I mean, what do I mean by this? So our sequence of remainders is this: b1, b2, b3, b4, and so on. So consider these pairs. So b1 comma b2 is a pair, then we have b2 comma b3, then b3 comma b4, and so on. So now each of these bi's, what are the possible values of bi's? Since it is a remainder when divided by m, each of these bi must lie between 0 and m minus 1. Okay, so then how many such pairs are possible? How many such pairs bi comma bi plus 1 can be possible? So now bi can take m possible values, and bi plus 1 can also take m possible values. So the total number of such possible pairs is how much? M square, right? M into m. So the number of possible pairs is m square. Okay, so which is finite. But then this sequence of pairs, it is an infinite sequence, right? So b1, b2, b2, b3, b3, b4, b4, b5, and so on. It's an infinite sequence, but the number of such pairs is only m square, which means that after a point of time we must have a repetition. So for example, b1 is actually 1, b2 is actually 1. This we know because the initial two terms of the sequence are both equal to 1. So both the first two remainders, regardless of any m, is 1. Right? So our first pair is 1 comma 1, and so on. Okay, so now the thing is that since the number of possible pairs is finite, so after a point of time there has to be a repetition. So for example, so consider the first time when there is a repetition. So we have b1, b2, b3, b4, and so on. So let's say the first repetition is like b4 and b5 repeats with something like b16 and b17. So there must be some repetition, right? So let's say the first time a repetition occurs, the first repetition is this b4, b5, and b16, b17. But then if you consider, so what does this mean? This means that b4 is equal to b16 and b5 is equal to b17. But in that case, consider b6 and b18. Can we say that these two must also be the same? So since b4 is equal to b16 and b5 is equal to b17, and now what is b6? b6 is just this thing, right? Okay, because why is this the case? Because a6 by definition of Fibonacci sequence, this is a5 plus a4. So this equality also holds modulo m. If we take the remainders must also satisfy this equality. That is b6 the remainder when b6 is divided by m, that is equal to the sum of the remainders when b4 and b5 are divided by m. Right, so for example, if b4 is equal to, let's say, 1 and b5 is, let's say, equal to 3 and m is equal to 6, then in that case b6 has to be equal to 4, and similarly b18 must also be equal to 4, and then similarly the sequence must repeat, because what is b7? B7 is just b5 plus b6 modulo m, and similarly b19 is also b17 plus b18 modulo m, and so on. So then we have a repetition. Okay, so hence this sequence is periodic. It must repeat after some point of time. So now the thing is that there are, so for example, in the case when we were considering m is equal to 6, this case was equal to 36. So which means the period of repetition can be as large as 36. That's why we were not being able to find it in such a small range, but it has to be periodic. After a point of time it must repeat. Okay, so okay. Okay, so now the next part says that for any m, we have to show that there is a term in the Fibonacci sequence that ends with m many zeros. So for any m, if we go sufficiently far along the Fibonacci sequence, then we will end up at a term that has at least that ends with m many zeros. Okay, now what does ending with m many zeros mean? That term is divisible by 10 to the power m, right? So
So the 36 is just for example of
yes,
6, right?
yes, 36 was just an example. Yeah. Okay, so we need to show that for any m, there will exist some term in the Fibonacci sequence that is divisible by 10 to the power m.
So in the first part, I didn't get the last sentence. That
Huh.
how do you say? But like, how do you prove that it is going to happen after some time?
Okay, so if you are taking these pairs, so the number of possible pairs is m square, which is finite. Okay, but this sequence is an infinite sequence, right? We have first b1 b2, then b2 b3 b3 b4 b4 b5 and so on. It's an infinite sequence, but the number of possible terms in this sequence is only m square. So hence there must be a repetition, because the number of possible things, the number of holes is finite and the number of pigeons is infinite. So which means there must be a hole wherein two pigeons, in fact infinite number of pigeons come. Like this is the infinite version of pigeonhole principle. If you go through the lectures, so because the
Yes.
number of terms is infinite, so which means there must be a repetition, and once there is a repetition, since the remainders, the value of a remainder is the sum of the previous two remainders modulo m, so which means this thing has to repeat. Okay,
A
so
value of the remainder is uh,
so
like
bi
m
is the,
divides
yes,
bi minus bi.
Sorry.
M divides Bi minus Ai.
No, no. So what? So bi is the remainder when ai is divided by m. Okay. So now, and what we needed to show was that in this sequence bi, which is b1, bi is nothing but ai modulo m. So in this sequence b1, b2, b3, b4, so all the terms of this sequence lie in the interval 0 to m minus 1, because these are remainders modulo m. So what we needed to show is that this sequence is a periodic sequence, that is after, so maybe it has a period of repetition 4, which means that b1, b2, b3, b4, and again the same sequence is repeating. So b5 is actually equal to b1, b6 is actually equal to b2, and so on. So there is some period that may be large, but there is some finite period. That is what we need to show. And for this, what are we doing is we are considering how many such pairs bi comma bi plus 1 are possible. So since each of these bi, there are m possible values from 0 to m minus 1, so the number of possible pairs is only m square, because bi can take m possible values, bi plus 1 can also take m possible values. So now we are again looking at this sequence of bi's, and we are considering these pairs b1, b2, b2, b3, b3, b4, and so on. There are infinite many pairs, but now since there are infinitely many pairs and only m square many possible values for a pair, which means a pair must repeat. So for example, maybe as I showed, that it may be the case that b4 and b5 is the same as, let's say, b16 and b17. This must happen. Like, this is an example, but yeah, since the number of such pairs is finite, so after some point some pair must repeat. But once we have one pair that repeats, then the next terms must also repeat, because b6 is nothing but the sum of b4 and b5, and b18 is also nothing but the sum of b4 and b5. Similarly, b7 is b5 plus b6, and b19 is b17 plus b18. So it has to be the same sequence. We have a repetition.
So, but for when we started writing the remainders for
Yes.
6,
Yes.
we got one twice in the beginning, and
Yes.
even in between we were getting a few ones, but
That is
that
fine.
didn't imply that it
Yes, yes. So,
repeated. Huh.
because m is equal to 6, so m square is 36. So if we write the first 36 terms, then you will surely get a repetition. You have to get a repetition. So just that we wrote only maybe 10 terms, so we were not getting a repetition. But yeah, if you write it long enough, there has to be some repetition, because the number of possible pairs is finite, only m square. So in fact, if you take the first m square plus 1 terms, there must be a repetition. This shows that. So if you take the first m square plus 1 terms, so there are m square plus 1 pairs and only m square many distinct wholes. So which means some pair must repeat. So if you had written the first 37 terms of that, then you must have found a repetition. Just that we were writing only 10 or 11 terms. That's why we were not
Yes.
getting. Okay. Okay. Okay, and now the second part says that for any integer m, we want to show that there is a term in the Fibonacci sequence that has m, that ends with m zeros. That is, it is divisible by 10 to the power m. Okay, so now again, what do? We consider the remainders modulo 10 to the power m. So previously we were considering remainders with respect to m. Now consider remainders with respect to 10 to the power m. So okay, so then again we have this b1 is equal to 1, then we have b2 is equal to 1, because the first two terms are 1, so the remainder is also 1, and then we have something like some b3, b4, b5, and so on. Okay, now since we had proved earlier that this is a repetitive sequence, so which means, so we have 1 1 and then something, but then after some time we must have the same sequence repeating here. That is, we must have 1 1 and then whatever was here we must have here, and so on, because it was a periodic sequence, we proved earlier. Okay, so which means after some point we must have two consecutive ones, because initially we had two consecutive ones and the sequence is periodic, so after some point we must have two consecutive ones again. So let us say bi is equal to bi plus 1 is equal to 1 for some I. So this is my bi and this is my bi plus 1. But then what can we say about bi minus 1? So since ai minus 1, so what is ai minus 1? By definition it is ai plus 1 minus ai, right? So because ai plus 1 is the sum of ai and ai minus 1, so ai minus 1 is this. So if we divide by m, we get bi minus 1, this is bi plus 1 minus bi modulo m. Okay, but then bi plus 1 and bi both are equal to 1, and so this is 0. So which means this term, the preceding term, must have been 0. So we get bi minus 1 congruent to 0 mod, and we are taking the remainders with respect to 10 to the power m. I'm sorry. But that is all we wanted. So bi minus 1 on division by 10 to the power m leaves remainder 0. So what does that mean? That 10 to the power m divides ai minus 1, because bi minus 1 was the remainder when ai minus 1 was divided by 10 to the power m. But that implies that 10 to the power m divides ai minus 1 and we are done. Okay, so what fact did we use here? That the sequence is repetitive. It must be periodic. So since it starts with 1 comma 1, the first two terms are 1 comma 1, then after some point also there must also be two consecutive ones. And once there are two consecutive ones, the preceding term, that must be 0, which means that the corresponding term in the Fibonacci sequence must be divisible by 10 to the power m. That is the solution. Okay.
So could you please show the second question for
Yes.
a minute?
Second question means second part of this or question 2?
Question 2.
Question 2, okay. Yes, yes, go ahead.
No, actually I missed this part, so I'm just going through.
Okay, so I can repeat once more. So here what did we want to show? That for any integer n, there exists a multiple of n that consists only of ones and zeros. That is what we wanted to show. So now again, whenever we want, so again when we divide some number by n, what are the possible remainders? 0, 1, 2 up to n minus 1. There are n possible remainders. So now if we can construct n plus 1 numbers, at least n plus 1 numbers, then by pigeonhole principle, since the number of remainders is n, so two of those
Your
numbers.
voice is not clear in between.
Oh, okay. Wait. Net is fine. Hello, is it fine now?
It is like you're talking from a far away place.
Okay, 1 minute. Okay, is it fine now?
Yes.
Okay, yeah, so what I am telling is, so when we are dividing some number by n, the possible remainders are 0, 1, 2 up to n minus 1. There are n possible remainders. So now ultimately what do we want? We want a multiple of n which satisfies some properties. That is, it consists only of ones and zeros. So then we have n holes here which are the remainders 0, 1, 2 up to n minus 1. So if we can construct some special n plus 1 numbers, then by pigeonhole principle, some two of them must belong to the same hole, and then their difference will be divisible by n. So we want to construct some n plus 1 numbers such that the difference of any two of them is just a sequence of ones and zeros. Then it is sufficient for us. And that is why we do this. We consider these n plus 1 numbers wherein the ith number is just one repeated I times. The first number is 1, second number is 2 ones, third number is 1, 1, 1, and so on. So these n plus 1 numbers, when we take the remainders modulo n, there are n possible remainders. So at least two of them must have the same remainder, and then their difference must be divisible by n. So but now if we take
So
the
why don't we take 0, 10, 110, 101?
uh, then if you take the difference of this, so for example, if you take, let's say, 100, and then if you subtract it with 10, so this is not a sequence of zeros and ones, this is 90. That is not allowed. That is why we took these special numbers, because we want this property, it has to be a sequence of ones and zeros. That is why we took these special numbers, so which
But
has
it's
the,
a sequence of ones and zeros, so
yes.
both should be there right in the sequence.
Sorry, what?
So then both should be there in the sequence, right?
No, no, we want to, so our final number is this quantity, is the difference of these two numbers. So these numbers we are just considering, like, for the sake of the problem, but our final number is this. It's the difference of some two numbers in this sequence that we considered. So our final number has zeros at the end, right? This is the number that we output. This is the multiple of n, which consists of ones and zeros,
Okay.
right? And we got this number by constructing this sequence. In this sequence we can do anything, like ultimately we have to arrive at a solution, but intermediate step we can do anything we like. So we constructed these numbers such that the difference of any two is a sequence of ones and zeros, and yeah, that's it. Okay. Okay, so yeah, so if you, yeah, yeah, if you have any more doubts, you can ask in the, this channel is this channel is there in NPTL, I think, wherein you can ask your doubts, or you can mail me personally also. Like, I think you must know my, or I am writing my email ID in the chat. You probably must know. Yeah, so this is my, yeah, I think I lost connection. Fine. So yeah, I've written my email ID in the chat. So if you have any doubts, you can mail me anytime. Okay. Okay. So we can stop now then.
Yes, sir. Thank you.
Yes, yes. Welcome.
Thank you, sir.
Okay.